Hi, and welcome to Dr. V's Chemistry Webcast. Today we're talking about how to do multi-step stoichiometry problems that go beyond mol-to-mol conversions. Here's what I'd like to accomplish in this webcast. First, I want to introduce the mol road. This is a visual approach to setting up these problems. And then we're going to use dimensional analysis to solve several different stoichiometry problems. Grams to mol problems, mol to gram problems, and grams to mol to grams problems. Notice they all have a mol to mol conversion. You'll need your calculator and your periodic table. Before we get out our calculator and start setting up a problem, let's talk about a strategy for handling these stoichiometry problems. First, it's really important that you read the problem carefully. That's always really necessary with word problems. And you need to start with a balanced equation, or none of this is going to work out the way you want. Once you've got that balanced equation, read the problem carefully, like I said, and list out what you know. Make sure you've identified what you're solving for and what information is provided in the problem. After that, you start to set up your factor label. You'll need a mole ratio from the balanced equation, and you'll need one or more molar masses depending on the problem. And when you go to set up the dimensional analysis, you're checking to make sure your units cancel out properly. Then we can substitute in all our values, get out our calculator, and actually figure out the answer. Make sure you report your answer with the appropriate units and the correct number of significant figures. Many of my students find that having a visual roadmap through these problems can be really helpful. Where do you start? Are you starting with grams or are you starting with moles? Where do you end? Are you ending with moles or are you ending with grams? Setting up all your conversions so they cancel out the way you need them to can be a very helpful thing. We've talked about a strategy, we've got our calculator, we've got our periodic table. Let's do a problem. That's what this is really all about, right? What mass of water would form if 0.92 moles of hydrofluoric acid react completely according to the equation below? The reaction written here is a skeleton equation. It's got the formulas of the reactants and the products, but it's not balanced. We know we need a balanced equation. That needs to be our first step before we go any further. Now that we've got it all balanced, we know that we're solving for grams of water. It asks for mass of water. And what we also know is that 0.92 moles of HF reacted. So we've got moles, we need to get to grams. We can't do this directly. We need to get from moles of HF to moles of water, and then we go to grams. Let's think about this in terms of the mole road. We've got moles of HF. I can use a mole to mole ratio from the balanced equation to get to moles of water. And the balanced equation tells us that 4 moles of HF react to give 2 moles of water. That leaves me with moles of H2O. And then I can use the molar mass of water to convert to grams of water. Note that whatever I've got in my numerator becomes the denominator of the next conversion factor, and that helps me to set everything up. So we're going from moles to grams. Let's do the problem out as a dimensional analysis setup. X grams of water equals what I'm given. X grams of water equals 0.92 moles of HF. I need to convert from moles to HF to moles of H2O. I'll do that with my mole ratio. 4 moles of HF to 2 moles of H2O, and I got the 4 and the 2 from the coefficients of the balanced equation. I now need to use the molar mass of water to find the final answer, which is grams. I do want to point out that the numerator here is 1 mole of H2O. A molar mass is always grams per 1 mole. This is a common mistake that students make. I don't want you to make it. Now that I've got everything set up, I see that the unit moles of HF cancels out, and the unit moles of H2O cancels out. This leaves me with the unit of grams, which is what I was solving for. So now I can get out my calculator and solve it. I get an answer of 8.3 grams. That seems reasonable. And I report my answer with 2 sig figs because I had 2 sig figs in the given value of 0.92 moles of HF. Let's do another problem together. How many moles of precipitate will form if 3.42 grams of sodium phosphate react completely according to the equation below? Again, it's another skeleton equation, so our first step really needs to be to balance it. Let's put in all the coefficients, and let's go back and look at the question itself and read it carefully. It asks for how many moles of precipitate will form. Well, the precipitate is the calcium phosphate. It's the solid that formed when this double displacement reaction occurred. We started with 3.42 grams of sodium phosphate, and we want to know how many moles of calcium phosphate will react. And so we're setting this problem up grams to moles to moles. We can't go directly from grams of sodium phosphate to moles of calcium phosphate. We need that mole to mole conversion. Let's think about it in terms of the mole road. I've got grams of sodium phosphate. I can multiply by 1 over the molar mass of sodium phosphate to get to moles of sodium phosphate. And then I can use the mol-to-mol ratio from the balanced equation, which will get me to moles of calcium phosphate. From the balanced equation, I get the mole ratio that I need. I have 2 moles of sodium phosphate forming 1 mole of calcium phosphate. So we now have a path through the problem. We convert our grams to moles, and then we convert moles of sodium phosphate to moles of calcium phosphate. Let's put it into action. X, what I'm solving for, equals what I'm given. X moles calcium phosphate equals 3.42 grams of sodium phosphate. I need the molar mass of sodium phosphate, which is 163.94 grams per 1 mole of sodium phosphate. So I'm going to put the grams of sodium phosphate in the denominator, and the numerator is 1 mole of sodium phosphate. And then I need to convert from moles of sodium phosphate to moles of calcium phosphate. Note that what I've got in the numerator becomes the denominator of the next conversion factor. That's how I know I've got my units set up correctly. Now I can see that the unit grams of sodium phosphate cancels out, and the unit moles of sodium phosphate cancels out. This leaves me with moles of calcium phosphate, which is what I wanted. I get out my calculator and I do my math, and I get an answer of 0.0104 moles of calcium phosphate. Now I'm reporting this with 3 sig figs because I had 3 sig figs in the given value of 3.42 grams. Let's do one more problem together. You might want to think about doing this problem on your own and then comparing your answer to mine. It's just a thought. What mass of carbon dioxide gas will be produced when 6.7 grams of liquid octane reacts completely according to the equation below? Another skeleton equation. You know I like those. I like to have you practice your balancing equation skills. That's got to be our first step, right? Balancing the equation. So let's put all those coefficients in. I've got my balanced equation. I'm given 6.7 grams of liquid octane. I want to know the mass of the carbon dioxide gas. Let's think about this from a mole road perspective. I've got grams of octane. I need to get to moles of octane. I'll do that by using the molar mass of octane. Now that I've got moles of octane, I can convert that to moles of CO2 using my mol-to-mol ratio. And then once I have moles of CO2, I can convert that to grams of CO2 again by using the molar mass. Notice that we're setting up the conversion factors so that the units I don't want cancel, and I'm left with the units that I'm looking for. And what am I looking for? Grams of CO2. Now that we've got a plan in place from the mole road, let's put it into action. X, what I'm solving for, equals what I'm given. That's how I always set up my factor label problems. X grams CO2 equals 6.7 grams of octane. I need the molar mass of octane, which is about 114.22 grams per 1 mole of octane. I need to set it up that the grams is in the denominator, 1 mole of octane in the numerator. Now I can use my mol-to-mol conversion from the balanced equation. I know there are 2 moles of octane to 16 moles of CO2. So I'll set up my conversion factor with 2 moles of octane in the denominator, 16 moles of CO2 in the numerator. That will leave me effectively with moles of CO2. And now I can multiply by the molar mass of CO2, which is about 44 grams. Set that up, 44 grams of CO2 per 1 mole of CO2. And now that I've got my dimensional analysis written out, I see, or can confirm, that the unit grams of octane cancel. The unit moles of octane cancels. The unit moles of CO2 cancels. I'm left with grams of CO2. I get out my calculator. I'm going to do all my math. I get an answer of 21 grams of CO2. I'm only allowed 2 sig figs because I had 2 sig figs in the given value of 6.7 grams. I hope you found this helpful. Stoichiometry is a really important skill for chemistry students at all levels. If you did find it helpful, please subscribe to my channel. Consider liking the video. Leave a comment for the video. Study chemistry every day. That's how you get better.